Hello everybody, this is JavaMonk, and today I would like to talk about 4-dimensional space, as well as 5-dimensional space, and dimensions beyond that. So, this here is a tesseract, or 4-dimensional cube. Or is it? No, really, it's actually not. This right here is not a tesseract. This is the shadow of a tesseract. A shadow of a 4-dimensional shape imprinted into a 3-dimensional world. You see, we as humans evolved in a 3-dimensional world. So we have eyes that can see in 3 dimensions. And so we can't see in 4 dimensions. Now, even though we can't see in 4 dimensions, we can still think in 4 dimensions. We can do things in 4 dimensions. And if we open our minds, we can experience 4 dimensions. I will be showcasing these higher dimensions in the context of card games and board games. I programmed a lot of card games and board games, including the higher dimensional ones, in Minecraft, so I will be using this for demonstration. If you have a Minecraft account, you can play these games as well on my public Minecraft server. I will also give advice to anybody who is thinking to program something in higher than 3 dimensions. So first, we're going to answer the question, what is a dimension? The definition of dimension that we are working with comes from linear algebra, which basically boils down to the question, how many different directions can you move? So, for example, a line is 1-dimensional, because if you live on the line, you can only move along that line. A sheet of paper is 2-dimensional, because you can move in 2 different or independent directions. So, we're gonna pause right here. This idea of independence is important, so let's talk in depth about that. We can encode direction as an arrow showing where to go. This is called a vector. A direction or a vector is independent, in the sense of linearly independent, from another collection of vectors if you are unable to express that vector as a combination of the others. To make a combination, you are allowed to stretch, flip, or move, or any combination of those 3, but you cannot rotate. So for example, this vector is dependent on this one because it's just the first one flipped the other way and stretched. This third vector is dependent on the first 2 because you can stretch and move the first 2 to align with the third. When any vector in a list is dependent, the whole list of vectors is going to be linearly dependent. Now, these 2 vectors here are independent from each other because you cannot flip or stretch one to get the other. When all the vectors in your list are independent, your list is what's known as linearly independent. So definition, the maximum number of independent directions/vectors that you can fit in a particular space is going to be the dimension of that space. So these drawings in the Paint program here are in 2-dimensional space because you can fit a maximum of 2 independent vectors. Notice how when I try to draw a third vector, it will be a combination of the previous 2 no matter what I try to draw. Our space, of our reality, as well as Minecraft's space, is 3-dimensional, because you can jump. And upwards and downwards is a third direction that is independent of the 2 used for horizontal movement. So now that we know what dimension is, we can think about what it means to have more than 3 dimensions. If you were in a 4-dimensional space, then you would be able to move in 4 independent directions. Oftentimes, this 4th dimension is labeled as time, because time is something that moves independently of your position in space. The problem with that idea is that it doesn't easily extend beyond 4 dimensions. So for now, we'll be thinking of 4D in the context of 4 independent directions that you can move in space, also known as 4 spatial dimensions. Now this brings up a bigger problem. You can't really fit that in our space. Our space is 3-dimensional, so a 4th independent direction is going to be quite literally outside of our world and even outside of our universe. But that's okay. A lot of the geometry that we're familiar with has analogues in 4 dimensions. And since we only care about spatial dimension, you can have as many dimensions as you please. There's loads of videos and articles about 4 and 5-dimensional objects, and I put one of my favorite visualizations of 4D space in the description. So now that we have a working definition of what a dimension is, let's go experience those 4 and 5 and 6 and beyond dimensions. Let's start this off with a classic puzzle game, Minesweeper. So in Minesweeper, you have a grid of squares, and you have stuff hidden in those squares. There will be mines distributed randomly throughout the grid, and your task is to figure out where all of them are. And if you reveal a mine, you explode, and you lose. So you don't want to do that. Instead, if you suspect a mine is at that square, you'll want to place a flag at that square to indicate that there might be a mine there. So if you don't reveal a mine, then you will reveal either a number or a blank space, like this. And if you reveal a blank space, then it will reveal nearby blank spaces. This one tells you that one of these spaces in a 3x3 square surrounding that number, one of these things is a mine. If this number was a 2, that means 2 of these spaces are going to be mines. And blank spaces mean there are 0 mines in that 3x3 area. So that's why it'll reveal all the adjacent blank squares, because there are no mines in the 3x3 square surrounding them. And so, by carefully revealing squares, you can use logic and these numbers here to reveal where all the mines are. Once you flag all the mines and reveal all the non-mines, you win. You've finished the grid. Now, there's all sorts of techniques and tricks and higher levels to solve with these puzzles, and people compete for how quickly they can actually solve Minesweeper puzzles. But notice, this is a 2-dimensional game. The interactions between the squares can occur along 2 independent directions, and each number is concerned with a 3x3 square surrounding that number. So now let's step it up to 3 dimensions. Here, you'll have cubes instead of squares, but it's the same mechanics. You reveal a number, and that number tells you how many mines are nearby. Now, what changes is that what nearby means, this 4 right here is looking at all of these squares, or these cubes, as well as these cubes, and this one, as well as this one. So it's searching in a 3x3x3 cube surrounding that number, and it's saying that there are 4 mines somewhere in this range here. There are 3D Minesweeper games out there that you can play on the web. In the Minecraft version, I have to give the player movement tokens so that way they can actually move up and down. So this way they can actually freely move up and down. And I'll admit I'm not very good at 3D Minesweeper. I just program these games. Whew. 3D Minesweeper is very difficult. But here you can see the numbers just float, and so do the flags. So now let's extend the game to 4 dimensions. You'll be given new movement tokens, which will allow you to move in that 4th new independent direction. And these banners here will tell you what coordinate you have in that new 4th direction. So there you go. You can move up, kind of up and down in 4 dimensions. I called it up and down just for lack of a better term because I'm not sure what else to call it. This is up, and this is down. So now the numbers here are looking in a 3x3x3x3 hypercube, so centered at that number. So here's what that looks like. It's looking, this 3 is saying there are 3 mines in any of these spaces, any of these spaces, none of these spaces, but any of these spaces, any of these flagged spaces, or any of these flagged spaces. There's a lot of spaces now where the number could be referring to a mine being there. But now that we have 4 dimensions, why stop at just 4? Why not also do 5 dimensions? So you get 2 new movement tokens, which lets you move in the 5th direction, which is going to be independent of the 4th direction here. So this is 5th directional movement. This is 4th directional movement, and you can see it is in fact independent. I have 2 banners here to indicate where your current position is in the 4th and 5th axes. Now this is going to run very slowly because my computer has a bit of difficulty running 2,000 different cubes. Go figure. Minecraft is not built to handle 2,000 cubes that all act like they're 5-dimensional. So I revealed 1 space here in the 2-2 room over here, and this one is referring to the following places with flags. So it's telling you have 1 mine in one of these flagged areas. Let's see. Yep, that room, not that one, but that room, that room, that room, that room, that room, and this one, and this one, and also this one. So in this way, you are essentially seeing a 3D slice of a 5-dimensional hypercube. And of course, we can do 6 dimensions as well. No problem whatsoever. You just get 2 new movement tokens for each new axis that you introduce. These numbers just tell you what coordinate you're at along the 4th, 5th, and 6th directions here. But otherwise, it's the same. The puzzle is going to get harder as you go higher in dimension, but the mechanics of movement are going to stay the same. Unfortunately, I'm not going to be able to actually flag all the spaces that are relevant here, simply because my computer can't handle that. Yeah, turns out Minecraft is not quite able to handle 4,000 different 6-dimensional cubes running simultaneously. Oops. But you see, it was never a question of whether or not we should. It was always a question of whether or not we could. And if anything, you can use this as a proof of concept that you can put 6 dimensions into Minecraft. And in fact, the sky's the limit. You can have as many dimensions as you want, because these are all spatial dimensions. Okay, I'd like to go backstage on this game of 4-dimensional Minesweeper. How exactly did I implement this? So, what I did is I quite literally copied the 3D puzzle room over here, and just copied it over and over, and arranged it in a line. And the movement tokens, all they do is they just move you between the rooms. That's it. That's all they do. Now take all those 3D rooms and arrange them as a flat grid like this, and now you have 5 dimensions. So 4 dimensions moves you this way to the next room, and 5 dimensions moves you this way between the rooms. Then take those 3D rooms and arrange them in this kind of cube grid shape, and now you have a 6-dimensional puzzle. 4th dimension moves you along this way, like that. 5th dimension moves you up and down, like this. Well, up and down between the rooms at least. And the 6th direction takes you this way, the 6th-dimensional movement token. So the next time your friends brag about how fast they managed to beat a Minesweeper puzzle, you can say, those are some nice times. Unfortunately, I am 512 parallel universes ahead of you. Now, I only implemented 6 dimensions on this Minecraft server, but again, the sky's the limit. The way that you would go further, if you want to do 7 dimensions, you can take those 6-dimensional cube grids and copy them and arrange them in a line. That gets you 7 dimensions. Arrange those 6-dimensional puzzles in the shape of a flat grid, now you have 8 dimensions. Put those in a cube grid, now you have 9 dimensions. And you can just keep going up like that. Take those 9-dimensional puzzles, arrange them in a line, you get 10 dimensions. And just keep going. Now you might claim, this is cheating, because Minecraft is still fundamentally a 3-dimensional game, and I have done nothing to change that. And you would be absolutely right. I did not change the fact that Minecraft is a 3-dimensional game. Just like how I did not change the fact that your eyes are based on 3 dimensions. But remember how dimension is defined. It's all about independent directions. Outside the game, you can move freely through this space and zip between the rooms and look all around however you please. But when you're inside the game, the only way to access those other rooms is to use the movement tokens. There is no other way. And so, because of the way these movement tokens work, you can't access this room without using the 5-dimensional token. No combination of the 4D or the up and down tokens, or just movement around the room with your player character. None of those can access this room, unless you use the movement token to actually go there. So, each pair of movement tokens here introduces an independent direction. Furthermore, even if you don't accept that the interface is 6-dimensional, or that the game is 6-dimensional, the geometry consequences certainly are 6-dimensional. So, notice, in 2 dimensions, a number clue here refers to 8 nearby squares. Like this. Each of these 8. So, you have 4 edges and 4 corners. 8 total spaces. In 3 dimensions, a number clue refers to 26 nearby cubes. That's 8 corners, 12 edges, 6 faces. It's the standard geometry of a cube. In 4 dimensions, you're looking at 80 cubes. In 5D, that's 242 nearby cubes. And in 6 dimensions, it's 728 cubes. It's going up by a multiple of 3 in each dimension, because that's just how the geometry of cubes works out. It's all about 3 to the power of the dimension minus 1, and you do minus 1 because that's the cube that you reveal to actually get the number. So, even though, technically speaking, you are still in 3-dimensional space, you still have to move and think and work with geometry in the 4 and 5 and 6-dimensional space. So now for the programming advice. If you want to make your own game or interface or whatever in higher than 3 dimensions, the key thing to remember is that 4 dimensions is nothing more than 3D over and over, like this. And 5 dimensions is nothing more than 4D over and over. And 6 dimensions is nothing more than 5D over and over. And for that matter, if you don't have the ability to do things in 3 dimensions, then 3 dimensions is nothing more than 2D over and over. So now, to properly make use of the space, and to make it intuitive for the user, and also intuitive to program, you need to know 2 things: where you are, and how to move. So, in the Minesweeper example, these banners right here will tell you what room you're in along the 4th, 5th, and 6th axes, just like this. To make sure that intuition is preserved, the movement between the rooms is going to preserve your position relative to the room. So notice if I'm standing in this corner of this 3D room right here, and I push the 4+ button, I'm in that same position relative to the rest of these cubes over here. Same happens if I do 5+, or 6+, or any combination. It's all the same. You are still in the same relative position within the room. Things like that are critical to being able to navigate a space like this, that's 6 or however many dimensions that you have. See, humans are very good at spatial reasoning in 2 and 3 dimensions, so take advantage of that. Now while I'm here on the soapbox, I'll give a personal opinion and also some personal recommendations and advice. Here's the advice. Rotation is very challenging to do in 4 dimensions and beyond. Translation along these new axes is going to be much easier to program, and it's also going to be easier to comprehend from the player's perspective. So don't implement rotation unless you absolutely have to or you really, really want to. Let your 3D eyes do that rotation. Do the translation part, but let your eyes do the rotation. Also, and we'll actually see this in our next game, you don't have to immerse the player into those 4 and 5 dimensions in order to make a 4 or 5-dimensional game. So, in the Minesweeper example, movement tokens are not the only way to do this. I could have also given the player a view like this, and just given the player the ability to select squares all the way over here. It's the same 5-dimensional game, and you're still dealing with the same 5-dimensional geometry, but the interface does not necessarily have to be 5-dimensional. And again, if you're doing something like this, the same principles apply. You need to label your rooms, so that way the player knows what they're selecting, and then you should arrange them in a way that it's clear what's intersecting with what. So for example, it would be very clear that a 2 showing up over there is going to be pointing at this room, that room, that room, that room, that room, that room, that room, and that room. All of these 9 rooms in this block here would all be impacted by a number showing up in there, as well as just the subsquares within the rooms there. So if you arrange the rooms in an intuitive way like this, that becomes pretty clear. So there you go. That is Minesweeper in 2, 3, 4, 5, and 6 dimensions. And the lesson to be learned, take advantage of your intuitive understanding of 2 and 3-dimensional space. That is how you navigate the higher dimensions. And there you go. That's Minesweeper. I started with this game because it was the simplest to demonstrate how things extend as you go in higher dimensions, and it also immerses you in the space so that you experience the geometry up close. Another example of a game that reaches higher dimensions is 5D chess with multiverse time travel. This is also a showcase of the principles of higher dimensions, as I described them, done in a fantastic way. This is a variant of chess where you have the standard movement on the board, just like this, and then pieces are also able to travel back in time to previous boards, like this. There's even a fun little animation that comes with actually moving the pieces back in time. Bam, just like that. When you go back in time, you branch things off into a different universe. And then pieces are also able to hop between universes like this. Let's do an exercise. How many dimensions does this game take place in? So we have a bird's eye view of the board, and we're able to drag that view in two independent directions, this way and this way. And so our point of view is two-dimensional. But as we demonstrated with the Minesweeper example, just because your point of view is two-dimensional does not mean that your game is two-dimensional. So we want to look at in what dimension does the gameplay take place in? In what dimension do the consequences take place in? So to do this, we need to take on the perspective of the pieces. So let's look at this board. On this board, you have two independent directions of movement here. The boards are then arranged according to time and universe. So that's two independent directions in which the boards can be placed. In total, the pieces end up moving in 4 dimensions, like this. And so the movement rules and consequences are based on 4-dimensional geometry. So actually that means that the game title is misleading. This chess variant is actually 4-dimensional, not 5-dimensional. I suppose the 5th dimension is the friends you make along the way. Now, notice how this interface works. First off, all the boards line up this way by taking place in the same time, and they all line up this way when they take place in the same universe. The game gives you an outside view of all the boards, which means that as the player, you experience 2 dimensions, thus allowing to take advantage of our intuitive understanding of 2-dimensional space. Now as for the piece movement, that is going to be 4-dimensional. Now there's flattened views, where a piece can move along the axes of time plus board, just like this, and they can also move in the directions of universe plus board. So this right here takes advantage of our intuitive understanding of 3D space. Now, I don't have this game implemented in Minecraft, so I'll leave a link to the Steam game. And if you want a tutorial on how exactly the pieces move, I put a link in the description for my favorite explainer at the moment. I suspect that the reason why this game is called 5D chess is because of the common thing that time is the 4th dimension. And so then universe would be the 5th dimension. But you really don't have to limit yourself in that way. You can say time is the 3rd dimension and universe is the 4th dimension, just like this, because the game is 4-dimensional. Now furthermore, the pieces move in those 4 dimensions as though they are spatial dimensions. So it's the game mechanics themselves that end up changing the meaning of those extra 2 dimensions, so that they behave like time and universe and whatever else. Plus you get all the fun animations for that. So it's kind of like how in our world, up and down is a spatial direction, and it just so happens that gravity acts in that direction so that it behaves like up and down. So that means over the course of the game, you'll be building relations between the different times and universes so that it acts like you're time traveling through the multiverse and creating timelines, but really it's the game mechanics limiting the piece's abilities to move freely in the time and universe directions. Okay, one last game that I want to show you. This game is called Projective Set. This is a card game which works in higher dimensions, but it does not require spatial movement in higher dimensions. Instead, it uses logic in higher dimensions. So here's what the cards look like. Here's how it works. Each card has 6 spaces, where there can be a colored dot or not. During the game, 7 cards are laid out here. Your goal is to find a set, which is a collection of cards where the total amount of each dot adds up to an even number. So for example, these 4 cards here make a set. You can see we have 2 reds, that's an even number, 2 blues, that's an even number, 2 oranges, and 2 purples, and we also, you see we have yellow and green here. We have 0 yellow, which is an even number, and we have 0 green, which is an even number. Quick side note before we continue. I see the occasional debate now and then that 0 is even, or 0 is odd, or 0 is both even and odd, or it's neither. So let's settle it. The definition of an even number is that its value is 2 times an integer. A number is odd if its value is 2 times an integer plus 1. And an integer is the number 0, 1, -1, 2, -2, so on in both directions. Basically, they're counting numbers and their negatives as well as 0. So the question is 0 even? What you do is you set up the equation 2 times something equals 0, and then you find that the thing that you can fill in to make that true is 0, and 0 is an integer. So the value 0 is 2 times an integer, so it's even. Now let's ask a similar question, is 0 odd? Set up the equation 2 times something plus 1 equals 0, and you find that the only way to make this true is to put -1/2 in there. And -1/2 is not an integer. So that means the value 0 is not 2 times an integer plus 1. So 0 is not odd. The thing about math is that as long as you agree to the same definition/rules, you will always reach the same conclusion. So if you disagree with this conclusion, you're working with a different rule set, and we need to get on the same page about that before we can continue. Now, by the way, this is also how you can resolve the quote-unquote ambiguous math problems that show up now and then. What you do, turn the division into multiplication, and then watch the ambiguity disappear. And if you disagree with how I did that, then you're playing by a different set of rules. And again, we need to get on the same page about that. Anyways, so once you find that set, you collect those cards, and new cards are placed down in their place. And then you go find another set. At the end of the game, everybody's sets are counted, and the winner is either whoever found the most sets or who picked up the most cards. It's up to the players to decide. So it's a fairly simple card game, but it has a lot of math packed into it. So let's dig into that a little bit. In the deck, you have every possible card that has or does not have that dot in a particular slot, except for the blank card. So in total, you have 63, or 2 to the 6 minus 1, cards in the deck. Now, the fun part about this game is that regardless of which 7 cards you place down, there will always be a set. How can we guarantee that? By using linear algebra. It all boils down to how many dimensions we have in our card game. So each card can be interpreted as a list with 6 slots. Each slot either has a 0 for no dot or 1 for a dot in that spot in the card. When you pick up a set, you can track the totals of each dot as a new list. So let's say we pick these 2 cards here. Then we have this resulting list. Now consider, we only care if the number of dots in our set is even. Whether the amount of dots is 0, 2, 4, etc. is irrelevant. So let's remove the irrelevant information. If we see an even number in the set total, we'll just make it a 0. So in this way, we treat 0, 2, 4, 6, and all even numbers as though they are the same number. Because as far as we're concerned, they might as well be. It's like how we say that the fractions 2/4 is the same as 1/2, because when it comes to how we actually use those fractions, they might as well be. Making every even number equal 0 has some interesting consequences. Addition still works, but we end up having slightly different results from what you might consider normal. 0 plus 1 is still 1, because if you have no dots and you add a dot, that's now 1 dot. But now, 1 plus 1 equals 0, because if you have a dot and you add that same dot, you have an even number of dots, which we already declared is the same as having 0 dots. So because of this, we will end up treating 3, 5, 7, etc. dots as though it was just 1 dot, because it's 1 away from having an even number or 0 dots. So every even number of dots is treated as having 0, and every odd number of dots is treated as having 1. What we just did here is establish a number system known as Z2, or integers modulo 2. Now you do that for each of the 6 slots where we can have dots, and now we have the space that is known as Z2 to the 6. And at this point we can also define what it means to add 2 cards together. That's just adding each dot according to its slot, 1 at a time, and then we turn all the even numbers into 0 and all the odd numbers into 1. Now this works because in the game, the slots don't interact with each other. we only care if the number of dots in each slot is an even number, or 0 dots as we've established. So back to our question, how many dimensions do we have? These 6 cards that I laid out right here all have a dot in one slot and no dot in any of the other slots. So it'll have a 1 in one slot and 0 in all the others. What that means is that if we added any of these cards together, they will never cancel out each other's dots. And that makes all of these independent. You can't construct one card by adding together the others. Here's another way to think about this. Adding a dot in a particular slot can be thought of as a movement in some direction corresponding to which dot it is. So this here establishes that there are 6 independent directions that you can move because each dot doesn't interact with the other dots. So we have at least 6 dimensions. But now, watch what happens if we throw in a 7th card. Let's say we grab this one right here. So this 7th card here can be expressed as a sum of the 6 that we already picked out. Specifically, it's the sum of this blue one, this red one, the orange one, and the green one. And so it is going to be dependent on all of these 6 right here. Now the thing is, there are only 6 dots on the card. So this will happen no matter which card we pick out of here. And so that means there are no more independent cards that you can draw, and so we can fit a maximum of 6 independent directions, and so we are playing in a 6-dimensional space. And that means any set of 7 cards, therefore, cannot have all 7 be independent of each other. So there's guaranteed to be a set where one card is expressible as a sum of the others. And so if you took that card and then added on all of the cards that added up to it, then you're going to get a list of all zeros, or a blank card. Notice here, the number of each dot is even, which we counted as 0. And so you will have found a set. And now you know how to prove that there is always a set, regardless of which 7 cards are placed on this table here. And so the game is to figure out, can you find that set before somebody else does? There's lots of other things that you can logic out within this game. So, for example, if you make sure that a set actually has cards, so you can't just not select anything and then claim that you win the set. See, invalid, because you actually have to select some cards. So as long as your set is non-empty, here's a question, a little bit of math homework to leave you with. What is the minimum number of cards that you need in order to make a set? And then also answer, why is that the minimum? I'll let you all work that out in the comments. So there you go. 3 games that you can play that make use of higher dimensions at varying levels of complexity. You have Projective Set, which makes use of linear algebra, but doesn't require knowledge of any of that. You have Minesweeper, which requires spatial reasoning and gives you the experience of working with cubes in high-dimensional space. And you have 5D chess with multiverse time travel, which is actually just 4-dimensional, and which is very accurately tagged as survival horror on Steam. You can play the first 2 games here on my Minecraft server. IP will be in the description. I live stream weekly on Fridays at 8 p.m. Pacific time, and that's where I will be actively working on adapting, programming, and playing card games and board games in Minecraft with you, the viewers. So also, leave a comment about any other high-dimensional games that you know, and I'll look into possibly adapting them to Minecraft. So, hopefully you all enjoyed the math explanation, and I'll see you next time.